space. And our program director itself, which is me, Cik Dayang Fazira binti Awang Simon, and all the participants for this event. Have you guys done filling out the entrance survey now? Or should we wait for some more? Space. And our program director itself, which is me, Cik Dayang Fazira binti Awang Simon, tell us, and you guys need more participants for this event to fill out the survey. Have you guys done filling out the entrance survey now? Or should we wait? Alright, I see some reaction here with thumbs up. Thank you guys. You guys are the best. Anyone care to join me? Open camera with Dr. He. Come, join me. Open camera, guys. Don't be shy. I feel like it's so hot today here. Anyone still need some time to fill out the survey? Or we could just proceed. All right. As I go and I see people giving thumbs up reaction. So before going any further, let us begin with the recitations of dua that will be led by Sharil Izzat bin Badrunizam. Calling for Sharil.
Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Wassalatu wassalamu ala ashrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. We express our gratitude to you for allowing us to attend the program of Selector Additive Manufacturing in Space on this wonderful morning. We ask you for the safety of our religion and the welfare of our body. Make the days that we've gone through, starting with your mercy, continue with your blessing, and ended with your forgiveness. Ya Allah, Ya Rahman, Ya Rahim, kindly give us strength and courage to face the struggle to find and gain knowledge. Kindly bestow us blessings, physical and spiritual health, fitness of mind, peace of mind, and strength of spirit. We seek your blessing for the flawless progress of this program from the beginning till the end. We seek your guidance to steer clear of events that would be detrimental to the progress of this event. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Sallallahu ala sayyidina Muhammad wa ala alihi washabihi wasallam walhamdulillahi rabbil alamin.
Amin, 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 ya Rabbal Alamin. Thank you, Sharil, for the prayers just now. Ladies and gentlemen, for your information, the purpose of this event is to explore cutting-edge advancement in space manufacturing. Professor Dr. Miranda Fateri has been a professor in the Faculty of Mechanical Engineering and Material Science at Aalen University since October 2019. She has devoted herself to 3D printing and, among other things, one of her new type research contribution is cost-efficient propulsion system based on pressurized air, which can be used for transporting construction parts. Without any hesitation, I would like to invite and welcome Professor Dr. Miranda Fateri, our guest speaker today, for her sharing session.
Thank you so much for introducing me. Welcome everybody to the lecture about the additive manufacturing space. And also thank you very much to the colleagues who are sitting here and put so much effort on making this lecture happen. I will share my screen. I hope everybody will be able to see it. Yes, okay, perfect. So I will start with the lecture. Before starting with the additive manufacturing, or the famous name in the market, another name for it, 3D printing, I want to give an overview on why are we focusing on 3D printing for space. So there are two purposes. One is the research in microgravity conditions, for example, on International Space Station, ISS, where astronauts are mainly doing research to understand the universe better. So we try to 3D print small objects which astronauts need on the space station. Why do we do that? Because transportation costs to the space station is relatively high. So you can see here on a kilo transportation of materials from Earth to ISS costs between $20,000 to $40,000. So it's a lot. And it happens also that under the microgravity conditions or weightlessness, astronauts lose tools, caps of some containers, and it's sometimes hard to follow the objects. So if they need some small parts, for example, out of plastics, it would be really great to be able to produce it, not sending it with a cargo to the space station, which cost a lot, and also it takes some time. Another purpose you can see here on the left, so you can see my mouse cursor, yes. So for long-term point of view or big image, we want to go to other planets, and Moon is the natural satellite of Earth, which could be used as a stopover. For example, if you want to go to Mars, it would be great to have a stopover on Moon as a tank station to tank, or also for the for studying the universe, like establishing telescope, astronomical centers to understand our universe better. So for midterm to long-term missions, we need infrastructures on the Moon, like roads, habitats, landing pads. And that's why we are going to focus on 3D printing or additive manufacturing, because it enables using the material which is already available on the Moon, for example, which we will discuss it later, and it's a fully automated process. So let's overview what is additive manufacturing, or also namely called 3D printing. Imagine your raw material as an apple. There are different manufacturing methods in the market. One of them is subtractive manufacturing. So if we extract one part of the apple, we will have a new shape of it. As I told you, this is called subtractive manufacturing. In market, you will see it as a CNC machine. You have a block of metal, and we will extract the parts that we don't need and have a new form. In this manufacturing method, we have lots of waste material. So this part of apple, which is already gone, is a waste. Second method is formative manufacturing. So we smash our apple, we have a new form. In industrial applications, You have a metallic sheet and you will bend it. You change the form of it, and you will create a new shape out of it. In additive manufacturing, as its name implies, we make the objects layer by layer. We add layers of the structures on top of each other. There are different methods of additive manufacturing, or namely called as 3D printing, how we create the layers and how we bond them together. You can have these layers made out of powders, filaments, solid sheets, and bond them using the heat, glues, and other techniques. So printing, what we need is, we need a CAD file, virtual model, which you can model it yourself using CAD files like SolidWorks, CATIA, or you can gain this data by 3D scanning of already existed object. Then we will give this data CAD file to a software which slices this model into different layers. So we break down our CAD file into layered models. And then we give this, this data to the machine, and the machine will try to make the layers and put them on top of each other. At the end, we have our physical prototypes. All in all, what we need for 3D printing is a CAD file, making layers, creating the layers, and joining the layers on top of each other. As you can see, it's almost a fully automated technique. That's why when we want to have a fully automated manufacturing process, 3D printing is a really good candidate for us. And please feel free to stop me if you have any questions anytime during the presentation. You don't have to wait till the end. So as I told you here, depending on how we make the layers and what kind of technique we use to join them, there are different 3D printing methods. Today, we will review the main methods. First one is called fused filament fabrication, or maybe you know this method in the market as FDM, fused deposition modeling. This is a brand name. This is a protected name of this technique. So what is fused filament fabrication technique? How does it work? As the name implies, we need filament for this fabrication technology. These filaments are available in the market from different types of plastics. Let's say a kilo around $30, the cost of these filaments. And we check these filaments and put it inside a nozzle. This is our nozzle, okay? And the filament will be heated up. We have a resistive heat here, will be softened by heating. And then the filament, which is already solid at top, you can see here, this will be pushed through, for example, one gear and one roller, which are moving in different directions. So through this movement, we push the filament down. The material here is already soft due to the heat, and we extrude it, right? So you can see here the extruded materials. And then the nozzle moves in X, Y, Z direction. We have different movement types. I don't want to go through that, but you can see here the nozzle moves in X, Y, Z direction, and the material will be extruded. We will first print one layer, and then the nozzle goes up, and we will have our 3D object. As I told you, the input material is in filament form, and we shape the layers using heat. So now the question is, if this is a simple geometry that you see here, but if you want to have more complicated geometries with the steep angles, for example, if I want to have this geometry here, right? So we said that we have to slice it to the layers, and this is my first layer, this is my second layer, third layer, and I go up. So if this object it's big, due to the gravity, it might collapse, right? Due to the weight. How can we avoid this collapse procedure? You know, on Earth, when we make buildings, we have some scaffolds. So we make the first floor, and then we make the scaffold. We jump on top of the second one, make the scaffold, and build the building completely, and then we remove this, right? Okay. We do the same thing in 3D printing. What we do is we make support material as a scaffold here. We make the main material. I slice this. And the first layer, this is support, and this is the main material. Support, main material. And after finishing, I remove this part. Okay, and part is finished. So that's why we will need two nozzles here, one for support material, one for main material, as you can see here. We have two filament colors, two nozzles here. Procedure is the same, and after the process is finished, we remove the support material. How do I remove it? Sometimes the support material is something like plastic glass, so you can break with hand, or they are water soluble. You put it in water, the support material will be gone. You can have a different application of these printed parts. You can make some functional parts, prototypes out of solid structures, or we can have also flexible plastic. As you can see here, this is a flexible part. We call this thermoplastic elastometers, TPE, so you can reshape it. Now the question is, what's the status for space? What can we print? This type of 3D printers has been launched to International Space Station on 2014, August 2014. The first company who sent this printer to space is called Made in Space Company. These are the colleagues from the Made in Space, and they tested these 3D printers under parabolic flight conditions, which we will discuss this later. And there is a functioning printer on ISS right now, which they can print PLA material out of it. This is astronaut Scott Kelly, American astronaut, which holds a 3D printed object in hand, and you can see it's floating under the zero gravity condition. Now, as the question is, when we think about printing in space, what is the main difference between the printing in space when there is no gravity, the object is floating, and printing under Earth conditions? So, you know, I told you that we have here a nozzle which we extrude the layers, right? On Earth, imagine this is a water droplet here. Due to the gravity, when I have one water droplet, it has a spherical shape, right? Due to gravity, the shape will change on Earth. If the gravity is too much, for example, okay, we have a gravity and also surface tension and interaction, like viscosity. Material has a viscosity, interaction forces and surface tension forces. If the weight of the particle, or let's say water droplet, is too little, the surface tension forces are dominant. So the shape of droplet will stay spherical. If the weight is too bigger than the surface tension forces, then the shape of the droplet will change a lot. So this has something to do with the viscosity. So this is a colored water and this is a honey on Earth. So the shape of a honey droplet and water droplet are different, right? If you put it on Earth. So we have some calculation methods on Earth how to predict this shape change of the material on Earth. I don't want to go through this. If someone is interested, they can write me later. I will send you the article. But in space, when there is no gravity, everything will have the spherical shape, right? Like a water droplet. So you can see the difference of 3D printed part on Earth, which you have 1G. So this is the X-ray data of parts when we print it on Earth. The layers look the same, and they have a little bit of change in their shape, right? On zero gravity, you can see here they have mostly spherical shapes, right? Because there is no gravity to push them down like a water droplet, right? To push them down shape, they change. So what's this effect? The adhesion between the layers will be different. So the mechanical properties could be different. This is what you see here is done on board of a parabolic flight. I will explain to you later how it works. But we could see the difference on that. And this is the side view of that. And if we have 2G, too much of gravity, the layers will be too much pressed against each other. So this is the first difference that we can see. The second difference is what will be about the supportive structure. On Earth, I need lots of supportive structure because due to the weight, the parts can collapse. When you don't have weight, so the part it keeps its shape. So I can tell you that we need very little supportive structure, and we need it because we want it to connect the part to the platform that we print, not that for avoiding it to fly away, right? Not for the weight of the part. So these are the things that you have to keep in mind. Printing on ISS is on using plastic is working very well. The mechanical properties of the part are comparable to the ones that we are printing on Earth, and with a little bit of adjustment and parameters, you can successfully print parts. Now, what about if we go to the moon? Can we use this technology or not? And if yes, what kind of material we want to use? So you know that the hot topic recently is sustainability. We don't want to use lots of plastic on Earth. When we don't want to use lots of plastic on Earth, we don't want to use it also on the moon, right? Also, it costs a lot for the transport. So what can we do? We thought of, can we use the material which is already available on the moon or not? What is available on the moon? Moon sand, right? So we thought, can we mix moon sand with plastic and make a composite filament out of it and 3D print by it? So before that, I want to tell you a little bit, maybe you have questions. So what is moon sand? Moon sand is very similar to volcanic ash on Earth, okay? It's black gray material, which is similar to volcanic ash. We brought almost 450 kilograms of actual lunar soil from Apollo missions back on Earth. And we already know what's the chemical properties of that. So we have artificial moon sand on Earth. These 450 kilograms are partially in museum. Some of them are gave as a gift to politicians. And if you want to have it for the experiments, we can have 1-2 grams of it. It would be really, really expensive. And 1-2 grams is not enough for our 3D printing experiments. So we have artificial moon sand that you can order from NASA, or in Europe we have also a source. Yeah, so we ordered one European one. We mixed it with flexible materials. Here is the plastic, and here is the moon sand, and we made our own filaments out of it. And afterwards, we showed that we can print on Earth plastic parts which are mixed with the moon sand. This is 10% moon sand of weight, 90% plastic, but we can mix it with higher weight percent mixtures. So what do we do? Then we will go on board of a parabolic flight. It's an airplane, okay? You go on the airplane and you install your experiment on that, and you are weightless, and then you can start your experiment. How does this the whole parabolic flight things work? So I have here better slides. So this is you're on board of an airplane, and then you have a steady flight, which here the gravity is 1G, normal gravity that we have. We fly for 1 minute here. Then the airplane changes its slope, and then when it goes really with a high steep angle, it feels like roller coaster. So you are having 2G. You will be, stuck to the plane. You can't even move your head. I don't recommend that. You feel bad. And then once you have this 47 degree, the pilot tells you have the microgravity. So you start so he brakes, and then you will be thrown, and you will be weightless. And for 22 seconds, you have the microgravity conditions, and then you go back down, then again 2G, you will be stuck, you will be on the floor, and then you have a steady flight 1G here, but this will continue 32 times, okay? So it's sometimes it's not that funny. When you go up, down, it won't be that funny. So what we did was we took our filament, we took a 3D printer here from Prusa Mendel. Maybe you know that. They were our sponsors, and they were kindly supported us during this project. We took 3 of them with us, 3 Prusa, and we needed to do some modifications. Unfortunately, we don't have much time to discuss the details. If you're interested, you can contact me. I will send you the details. And we tried to print some parts for mechanical properties, evaluations, and stuff like this. So I have a video here, which I will delete my note here. You can see the video, which shows you how microgravity feels. This is my student, Konstantin Schuler. He's a master's student. I flew with 2 students of mine. So this is in lunar gravity, okay? We went to lunar gravity, and you can see how the cell phone floats. And then this is 2G, so he cannot throw the cell phone again. This is, I will play it again so you can see the difference better. So now we are in this phase of free floating. And then we go to this phase, which is 2G, and he can't throw this, it will be stuck. So that's it. And yeah, all the gravity profile will be recorded. We have accelerometers on the plane, and you can record all the information. So what did we see? This is the cross-section of parts that we printed. These white ones are moon sand. The gray one is plastic, TPE. This one is moon sand. This is printed under lunar gravity. This is printed on the Earth gravity. You see on the Earth gravity, these are the layers. They are all connected together. These ones are normal. On Earth, we have it. This is from the software. And then on the moon, the gravity is less. So the layers are wavy. We have more porosity here. You see? I have to tell you that this flight campaign was last April. It was less than a year. We're still analyzing the results. I don't have all of it. We are still doing 3D scannings. These are just primary results that I had, and I thought it would be interesting to show it to you. So why do we need this? Because we can analyze in advance if the mechanical properties are good enough to be used on the moon or not, for what kind of application we need it, what kind of modification we can use it. And then based on these results, if we see we need more exploration, we can always apply for another flight. So yeah, that was from the FDM. Does anybody have a question? No? Yes? Okay. So I go to the second. So we reviewed together the fuse layer manufacturing or fuse filament fabrication. And now I want to go to the second 3D printing techniques, which is called selective laser sintering, SLS, or selective laser melting. How does this process work on Earth? Let's say first. So we have 2 containers. One of them is filled with powder. It's a powder-based process. So instead of filament, we have powder now. And then imagine you have a iron powder, stainless steel powder. And this container is collected to elevator. It goes up to one specific layer thickness. Then I have a roller, which brings the powder on top of a building platform. We say this is a building platform, okay? You can see now from the beginning better. So we bring one layer. Then number 1 is laser here. I have a laser source. Here I have a scanner system, so it's mirror, which projects the layers on the powder, okay? And we melt the area, or we sinter the powder in areas that we need. And after the process is finished, we can take the part out of the powder bed. We can have sintering of plastics, melting of metals. This is an example of the part which was printed using this technique. I will show you a video of like how this process works. So you have one layer of powder. This is a cobalt chromium powder. Laser starts melting the areas that we need. Okay, first the contours outside, then inside. Here is the building platform. Then it goes down. You don't see that it goes down because it's only 45 micrometers, so you can't see it. And then the powder, we will bring the next layer. The powder is stored between these two blades. One of them goes up, we bring the powder, then it goes down. The other one goes up, we bring the powder. This is the smallest machine available in the market. So let me stop here so you can see it better. Okay, it fits on a table, office table. You have your software computer, and then this is the building chamber. You have a microscope that with the filter, you can see the process inside. These are the gloves that you can, afterwards work inside the machine and remove your parts. Powder overflows goes here, powder containers, like you can pump the powder inside. And layer thickness, you can see each layer is around like 20 to 50 micrometers. And the machine costs around 150,000 euros, the process inside. And I will continue here, you can see the process better. The building platform here is round and it's about 7 centimeter in diameter. So it's almost like this. And yeah. So that's basically it. You can see here, this is a slow motion of video of the process. What's really interesting here to see is once you melt the parts, there are lots of particles which are ejected from the powder. Smaller powder particles due to the heat. We have, I have to tell you, in the chamber, we have, if you want to manufacture metallic parts, you have inert gas like argon, nitrogen, helium inside the chamber in order to avoid the oxidization, right? And also in this process, as you saw, we have some particles which are ejected. So the shielding gas, I will show it to you how it inside the machine looks like. So you have a shielding gas that takes these particles which are ejected with itself, goes inside the filter, the particles will be stuck here, and the gas will be pumped again inside the machine. Okay, so we need the shielding gas for almost two reasons. Argon, nitrogen, helium we can use. It avoids oxidization and it removes vaporized materials and distract the splashes. So now the question is, can we use this method on microgravity on ISS? Is it possible to use it or not? Because if I bring one layer of, let's see here, I will replay it again. If I bring with the powder here, the powder will start floating all over, right? So how can we fix the powder to avoid it floating? I'll give you 30 seconds to think about a solution. Yes? A binder, thank you very much. So one of your colleagues said that we can use binder. That is correct, we can use a binder. But what if I don't want to use binder because it costs, for transporting it is extra material? Okay, yes. I see there are lots of ideas here and there are lots of nice ideas. Yes, it could be. Let's say I want to print only metallic parts. Some people maybe say, what about magnetic things? Yes, it works, but what if I have a powder which is not magnetic? And so there is a solution which I talked about the gas, inert gas. And you saw here, we pump the gas from the left side, right, to the right side, and take the particles out and pump it again. What if instead of this, I pump the gas from the top and push the particles on the platform? It avoids for the particles to float. So that was done in BAM Berlin. Professor Jens Gunster is a colleague of mine. So what they did is they put the gas flow on top. You have the first, it's better that so this is the building platform. I have the first layer of powder, and I pump the gas here, and I push the particles to the platform. Well, what we need to think about is the platform should be also porous, as you can see here, that the gas goes inside the powder and comes out and will be pumped again, right? So using this technique, they could print under microgravity 30 layers. So these are printed parts. The qualities are also perfect. But the disadvantage is you cannot have a big part printed using this, because if you have here thousands of layers, it takes lots of time for gas to go through this. It might be that it gets stuck somewhere, right? So the efficiency. But for thin parts, it's possible. And another thing is, I told you that you saw this video that there is, sorry. In this one, you saw that there are particles ejecting from, right? So in this case, if the particles are ejecting, the gas will, push them on the surface. And what happens? The surface might have some defects of the particles. So these are things that we have to keep in mind. But basically, for thin particles, it's possible to do that. Okay, can I use this on the moon? The laser melting, this technique. So on the moon, I have gravity. It's less than Earth. So powder will be stuck to the platform. It's easier to make cows out of it, but it will be stuck. Now the question is, can we use moon sand to melt and 3D print objects? Okay, because it's the material which is available in the powder on the moon. So I did this study during my PhD, and I ordered artificial moon sand from NASA Johnson Center. You can see it here. This is under the microscope. It has sharp edges, random particle shapes, different minerals inside it. So what I did was I started to melt 1 layers with different laser power speed, and studied them on the microscope. I made 1 layers to test. I have 2 papers on this. If anybody's interested, I can send you the details. I tested if it's basically possible to do that. And what I did was also pressing the powder and putting in the oven and filming it, and see how the melting behavior is. I love this video. You can see the particles are start to melting from the top side, and you can see how the powder is swallowed inside. And then you have a spherical form, and due to the gravity, it starts floating. So it makes a half sphere, and this is a flow temperature. So I knew already what white temperature it's melting and what kind of laser power I have to lose to do this. So you can see here again, how it starts melting and how it swallows the powder particles underneath, and how the shape changes under the gravity forms. So at the end, I think after a few months of fighting with the parameters, I could make these objects, which I think they look beautiful, shiny, but they are brittle because they are something like glass and ceramic. Okay, a volcanic ash is basically ash, right? It's not something that you can make. One of you said binder. Yes, with binder you can make really structures like beton. Beton is German.
Bentonite.
No, not cement. Blocks of buildings, like something like clay, but it has other name. It's concrete. Thank you. Yes, concrete. I'm sorry. Yes, concrete structures. But this study showed that it's basically possible to use it, but mechanical properties were not necessarily. If we use only small lasers, there were cracks in the part with this process. So what we did is, after that, this was my postdoc project. We thought that, okay, laser is great, we can use it, but actually on the moon we have lots of sunlight. You don't have also air, and that's why you don't have clouds. The sun is always constant. I mean, you're in Malaysia, you have always sun. In Germany, no, we don't have it. So it was very hard to use the sun and concentrated with big mirrors to print objects. That's why we didn't use actual sunlight, because as I told you, it's when the clouds come, the intensity changes. Then we use artificial sunlight, which is xenon lamps. We had these lamps. They had the same intensity of the sunlight. We concentrated on a flat mirror here, flat mirror. We were projecting it inside a vacuum chamber. And then we had a small 3D printer inside it, so 3D print object. So, and after that, so you can see moon sand inside the solar 3D printer. We print some object. We cut them to make the parts for mechanical test. Then after that, we gave the results to our civil engineers and architects, and they could say, okay, what can we build on the moon with this material? So these are the parts that we printed under ambient condition, and the vacuum was really complicated. The problem is inside the moon sand, we have gas, and then when you heat it up under vacuum, the gas starts to come out and makes the process very, very complicated. That's why we followed this study with another project, which was 2 years ago. So in this study, instead of having small laser, we had a big laser, a laser with a very big spot size, like 10 centimeters. The spot size was like this, and it has the same intensity as the sunlight, which it was a demonstrator, and we started to melt big objects. We wanted to make roads and say, you know, the parts that I did here, you can see they fit in my hand. They're really small. And then we said, what if we want to have roads, habitats? So we need really big object. If I want to use a very small laser, it takes ages to finish it. So I will show you here the video. Here is the laser. And we tried to make these elements, which we call that interlocking elements. You see that in your gardens, probably, these elements that you walk on it. And you can see here how big the laser spot is and how we are melting the moon sand to make the paving elements out of this. It was a 12 kilowatt laser, CO2, yes. And we wanted to make these elements because if we make roads using this, and if one of them breaks, the cracks does not propagate. We can replace it, right? And the other thing was, because it's glass, when you melt one line and you remelt the second one, the other one starts cracking. It's glass. So we made these interlocking elements. You can see it's open here, so we don't have any overlap to remelt any line, and you can put them beside each other. So it was a big project between BAM in Berlin, TU Clausthal, Hochschule Aalen, Liquid System, and it was funded by European Space Agency. And at the end, we have a compressive strength in average of almost 90 megapascal, which is comparable to concrete. It's glassy objects on the top, but it was massive. Yeah. Last but not least, we can use also microwave heat to melt moon sand. This is really crazy. This is a kitchen microwave, okay? The kitchen microwave you have in your kitchen. And, you know, if you look at your kitchen microwaves, you have inside a plate, right? And you put, I don't know, a bottle of milk inside, and this plate starts turning. Have you wondered why? Why the plate inside microwave needs to turn? Why can't you just put your glass there? And yes, why equally heat up? Like what if I put it just my glass there? Because microwaves, kitchen microwaves has 3 spots which has a high intensity like laser, right? So we call that microwave hot spot. And then your table would turn to equally heat up this. So how do you find out these spots? You can do the experiment home. Take the plate out, put one thin bread inside it that doesn't burn, that doesn't turn. turn your microwave on, and after 2 minutes, turn it off. It depends on of course, the power. And then you will see 3 spots on your bread, which is burned. So these are the 3 areas of the microwave. So what we did here, we actually took a microwave, kitchen microwave. We found these spots, and we put the moon sand particles inside. And the beauty about the microwave is also when you have your, for example, bowl of milk. Sometimes inside of milk is hot, outside is cold, because microwave penetrates inside the material and heat it from inside to outside, can heat it. So that's why when you put the moon sand block already sintered inside, you can see it glows from inside. It's not like the laser that you will hit it from the only outside. So conventional heating methods, you heat from outside to inside. Microwave can penetrate and heat from inside to outside. That was really something that we wanted to investigate, how it interacts with the moon sand, and it worked. And this is a suggestion from colleagues from NASA to build up a 3D printer which works with the microwave heat. This was only, I wanted to tell you that it's not only laser, sunlight, binders, but also microwave. So all in all, the parts that we made, I told you, it's like glass and ceramic, and it cracks. It's like a bottle of water, Coke, beer, that if you don't cool it down properly in the industry, it cracks. So how can we avoid this crack formation? In the glass industry, when you melt the glass, you will leave it for some time in under the glass transition temperature. I don't know if you're familiar with this term, glass transition temperature, or TG. You can Google TG. What is TG? Glass transition temperature. You have to leave your part inside that, and the stress will be released, okay, and the part doesn't crack. But if you heat up and cool it down immediately, then it will crack. So we thought of all of the parts that we made so far, the cooling rate was not controlled. So why not melting the moon sand inside an oven and cool it down with a controlled temperature? This is a work of student of mine, or 3 students of mine. So what we did here is we bought an oven. We removed the door. We cut inside and put a building platform inside that can move inside this cooling oven. We built a head. Why not melting the moon sand? And in this head, we have a print head, which put the moon sand. We put the moon sand inside it, and using the induction, this is the print head. Okay, let's see. This is the oven. We cut the bottom. We put the platform inside. You can see how the platform moves. It can go in X, Y, Z direction. Now it's moving slowly up. Everything is out of titanium because it has to survive the hot temperature in the oven. And you can see the building platform is moving inside. Then we have the induction coil here on the top, which we will melt the moon sand with it. And we have the oven here. The heating elements will be on. You can see it here. It is on. The part will be printed and then cooled down inside this oven in order to have a really, really robust and crack-free part. We were able to, during our last project, to make glass parts. You can see here how the parts are made. So this one, I will stop this. But you can see here, we extrude the glass layers slowly, and we can make beautiful objects out of it. You can see here and down here, this is the thermal camera, and we reached 1200 degree with that. This is a borosilicate glass that we printed. And something that is really beautiful, and it surprised me, is look at this object. This is printed without any supporter structure. So if the glass, you control the cooling down, and it reaches a certain viscosity, it cools down so properly that you don't need supporter structure, and you can make spring-like structures, helical structures like that. So next step is to put the moon sand inside and I think end of March, when I'm back, we will test the moon sand. So maybe next year I can present those results. So that was for the selective laser melting. Now we go to another process, which is called powder binder bonding, or powder binder jetting. Maybe you know this process. How does it work? I'm sorry, this is in German. So you have a printhead. Druckkopf here is printhead. This is a printhead that you have in your office to print your images, papers. Inside this printhead, you have in your office printers, you have colors, right? Ink. Now here we have ink, color plus glue. Imagine you have glue, right? And the rest is like this SLM. You have powder. You will bring the powder using a roller on top of the platform, and you eject glue in the areas that you need. When the platform goes down, you bring another layer, and then you add glue. And if your glue is colored, you can have at the end a continuously colored part. So this is made like this, right? Each layer was a powder first, and then we bring different color of glue on the areas that we need. I will show you a video how this process works. This process was, these are the example of parts that you can print using this technology. You know, it's all colorful. First printer in the market was called Z Corp. This process was patented in MIT in US. And I will go further that you can see the process. So using the software, you can locate your part. It can have colors. Everything is managed using a USB stick and a small LCD. This is the glue that you put inside the machine. And then these are the ink colors that you have in your printers. You import the part. This is the printhead. It's very similar to the printers you have in your machines. Instead of paper, you have powder here. Okay, so you print your parts, and then after the prints are finished, you can see you have different colors. So you have to take it out of this powder bed. You have a vacuum cleaner from the downside, and also from the top that will extract the powder. The building platform has holes for the powder to be extracted. And then afterwards, you have to remove the powder around the parts using an air jet. And because the powder is, the part is only connected with glue, the mechanical property is not good. So that's why we put the part that we print afterwards inside the glue again. Let it dry to make sure that the mechanical properties are good enough. Okay, so afterwards we add glue to it, and sometimes with brush. So you have to do it with love and patience, because otherwise the glue is very viscous and you can make bubbles on the part. So this is the process. I hope that is clear for everyone how it works. Now the question is, can I use it on the moon or not? Before that, we will look at if we could use this to build houses on Earth. The first 3D printed house on Earth was done using this technique. It was done in Italy, and you can see here the house was built, and it's located, I think, in a park in Italy now. The thing is, did you see I showed you the post-processing, like you add extra glue. Imagine for the whole house, you need to add it. It takes lots of time and to remove and cleaning it. So you can see here how much powder is all around. It took 3 weeks for this structure to do the post-processing. So it's not very efficient to do that on Earth. And if you have big houses, you know, you have to transport lots of sand with you. So what about on the moon or Mars? Do you think this process will work to add binder? Because we have vacuum, right? If you add water, fluid, it will be evaporated directly or frozen. So basically this won't work. But the European Space Agency made this beautiful object. It's 1.5 ton using this technique. And so they thought, okay, how can we solve the problem of the vacuum? So they made this nozzle. So if this is the powder, moon sand, the nozzle looks like this. So the nozzle tips goes inside and we eject the glue inside the powder. So it's not in direct contact with vacuum, and they add some chemicals. So it's not only the fluid binder, they added some magnesium oxide in it that chemically binds, reacts with the powder. And this is done, tested in the vacuum, and they could make some small smart parts to show that, okay, it's basically possible. Another thing that we need to be careful of is this video. You can see in this video, this is an astronaut having a brush and is trying to clean his colleague's suit and space suit and the helmet. Why is that? It's because moon sand is extremely abrasive, electrostatically charged due to the high energy particles and it's highly magnetic. It sticks to everywhere and it can damage the astronaut suits, rovers, electronics. Also for 3D printing, please look at this picture. So usually we won't have a smooth layer for laser, sunlight, binder, whatever to go through it. And because moon sand sticks together, it's very hard to make this layer. Okay, so there are lots of studies to show that what kind of layering system we can use to bring a smooth layer. This is like with a this is done with a vibration spreader. This is another one which we put the powder inside and using we let it to flow using its weight and press it a little bit. So I wanted to tell you that these are also challenges that you have to think when you go to the 3D printing parts. There is another technique. I'm jumping from powder binder bonding to stereolithography. Stereolithography, we don't use filament, we don't use powder, we use fluid resin in that. And so it works like this. You have a container filled with resin. Then you have a building platform here. Building platform has holes like this. And you have a laser source. Let's say here's a laser. And again, a mirror here, and it reflects the light here. We use UV light. And we cure or solidify the areas that we need. So this resin is sensitive to UV light and it will be cured. And then we go one layer down and the fluid comes up also from these holes. And we have our 3D object at the end. This is the UV laser, the resin is inside. This is the building platform with the holes. And then we cure one layer, we go down, and then we bring another layer, and we have wiper in order to, because resin is viscose, to make the surface flat, okay? I will show you how this process works. Stereolithography, or SLA, basically works with resin, which is sensitive to the UV light. So you can see here a little bit of this viscose resin. We expose it to the UV light. And then after, depending on the intensity, after a few minutes, or it's hot. I can tell you that maybe ladies know when you do nails in the studios, you put your hands inside this UV light. That's the same thing. It's the same concept. So yeah, you make the object layer by layer using this technique. And this is the punctual laser. So you solidify it layer by layer, point by point. And afterwards, you have your 3D printed object. Yeah, and then you have to remove your part from the resin, clean it, because all around your part will be sticky, full with the resin. You can see it now, the life. This is a very old machine, actually. So you will cure first the outside parts and the inside. So you can't see much here because the resin is transparent, basically. The UV light is, it's ultraviolet color. Now it's the layering. You can see the part is, the building platform is going down. And then once this is where the laser is. Once the print is finished, you can see it comes out of a resin bath. The building platform has holes for the resin to this part again to comes out, and then you have to remove your part from your building platform. So I don't want to go through the applications of this in the industry, but can we use this for the moon? The answer is, of course, resin is also plastic. It costs the transportation cost, and this is not recyclable, fillable, it's not sustainable. So that's why it should be necessarily mixed with moon sand in order for us to make it sustainable for the moon. So a colleague from Austria, from the Litos company, ESA funded project, they mixed the moon sand with this resin and printed the parts. They put it inside the oven, and then they removed the binder, and then you can see they made really precise and beautiful parts out of it, ceramic parts. So we can also use this one on the moon. All in all, it was my lecture today was a general overview of what can be done, what can we do for ISS and for lunar missions. There are our colleagues in my colleagues in Cologne. They are building a Luna facility. What is this? This is an inflatable dome. Inside we have artificial moon sand. It's dark on like the moon, so it has this solar light inside it. You can hang astronauts from spring, so they can jump. You can have rovers with different slopes and see how the movement of the wheels, or we want to put 3D printers inside it. This is basically a training facility, and also it inspires students. And it is also connected to a small lunar laboratory. So what are we expecting in future on the moon and that? So thank you so much. Please feel free to ask questions.
All right. Thank you so much, Professor Dr.
I think the lady is talking.
Oh, I was saying thank you for sharing just now. It's very impressive. I'm really interested in the Luna facility. I would like to go with German.
Yes, I hope
to see it for myself.
Yes, it's not finished yet. Hopefully in 1-2 years, if it's finished, would be great to have you guys there. I mean, I'm not directly working with them. I'm not working in Cologne, but I have colleagues that yeah, we can make contacts and bring you there.
Oh, I see. Okay. So right now, is anyone in the participant have any question? Since our event reached its climax, it's time to acknowledge and appreciate the valuable knowledge and lesson that we have learned today. It's pretty impressive, right, guys? We also get to learn 3D printing, and then we get to know the moon sand materials and lots of very impressive things. And then today, we have the privilege of learning from Professor Dr. Ing Miranda Fateri for wisdom and experience. She has enlightened us with her extensive knowledge and captivating presentation. So, any participant would like to ask a few questions regarding the topic? Or you guys can maybe anyone that viewing in our live YouTube channel, we will also be there and forward your questions to Dr. here. Anyone? I think I have some.
What are the chemical composition available within the moon sand? Okay, that's a very good question. So moon sand, let me then share another presentation. just quickly. I have another slide which can answer this question. So can you see? Yes, let's see, you can see. So I think everybody knows this famous picture of the Neil Armstrong footprint, and you can see that we are dealing with very fine particles on the moon. It can be compressed easily. If we look at the surface on the moon, it has two colors, right? So we believe that Galileo was one of the first people who made a telescope and could look at the moon. And then he saw these dark areas, which he initially thought it's ocean, it's sea. So he called it mare. In Italian, mare means sea, ocean. We still call these areas mare in English, sea. And the other areas which are have a lighter color are highlands, like mountains, hills. And later, when we had the Apollo missions, we took samples. And we understood that also from robotic missions. Basically, moon sand is made out of different mineral oxides like SiO2, aluminum oxide, calcium oxide, iron oxide, magnesium oxide, titanium oxide, and so on, right? But the chemical composition of highlands and mare are a little bit different. So the highland, which has a lighter color, is more enriched in calcium oxide, which has also lighter color. And the darker areas, it has more titanium oxide, which has a darker color. Also, we know that these are craters and the light will be stocked in it. So that also gives a darker view of it, and the origin of formation of those are a little bit different. But I wanted to explain that we have two different lunar sands, two categories. All of these two are made of different mineral oxide. This is similar, but have different contents of metallic parts. The mare one melts around 1200 degrees. The highland one, due to the calcium oxide, melts around 1400 degrees. So the melting temperature is a little bit higher. Yes? Yes. There's another question?
Yeah, there's another question in the chat from Azri Rahimi. Is it possible to do wire additive manufacturing in space?
Wire additive manufacturing in space? Yes, that's actually also a very good question, because I think last week we sent the first wire-based 3D printer to ISS. You know, we talked about, okay, selective laser melting, the powder will be floating. Wire won't fly, at least if you connect it. So yes, it is possible. European Space Agency invested a lot in that, and the first one was launched there. I didn't add it to my presentation, which actually here at your university, you have lots of LMD machines, I guess. Yeah, but yes, this is possible.
All right. I also have some questions from the committee itself of IMECI. As you know, we are IMECI, Institute of Mechanical Engineering of UITM, are globally situated, right? Therefore, I would like to get to know if there is any possible collaboration to be held between our university, perhaps. The event purpose simply to allow guests to network with each other in their field or community members. If yes, what is your recommendation?
Yes, so biggest part of my purpose of my trip was to establish such collaboration. There's a big interest from our side, and I see also from your side. Students are more than welcome to visit us during internships, bachelor thesis, master thesis, or even only in frame of Erasmus program to attend in our English lectures. We offer also language courses at the university, master thesis, or also PhD researchers are more than welcome. I'm in contact with Professor Jupiter, and we're trying to make this official, these contracts. And so you have my email address at the end of my presentation. I'm on the board, international board of the Mechanical Engineering Department. So you can directly contact me if there is any interest, personal interest in that, and I can forward your documents to the responsible persons at the university. But you're more than welcome to visit us.
We would really love to visit Germany one day.
Hopefully soon. I see hearts.
Yeah. So don't forget to follow us in our social media. So we will keep updating you guys regarding, who knows, we're gonna go to visit Germany soon, right, guys?
Or we will see each other on the moon.
Yeah, perhaps.
Thank you so much for having me. I really enjoyed it.
You're welcome. I think I have another questions from another committee member. They ask, are there any sustainability aspect to consider when employing additive manufacturing technology in space?
Yes, very much actually. So that's why we want to use moon sand as much as possible, the material which is already available there. We mix it with plastic, with resins, and also we can extract oxygen from the moon sand as breathable oxygens for the habitat astronauts. And also we can extract metals from the moon sand. Also, something really interesting from my point of view is, so we have lots of satellites turning around the moon and they are crashed. We have old Apollo spacecraft. The question is, they have lots of aluminium inside, aluminium oxides, metallic parts inside it, gold inside it. If we go back, do we want to put them in a museum from the first, landing history, or we want to crash them, melt them, and reuse the material? So these are all under the decisions. But I think, from my point of view, we will keep some stuff for memory, but lots of other satellites, robots that we have will be also recycled to be used for a lunar industry later. Yes.
I see. So that's how it works. See. And then there's also another questions regarding, I got it from WhatsApp group. They ask, how can 3D printing contribute to more efficient and cost-efficient, more effective and cost-effective in the process?
So right now, it's not the most, on Earth, it's not the most cost-effective process because it's not suitable for the serial production. It's more for the individual customized products right now. Researchers are working to make that happen for a series of serial production. For example, right now we have SLM printers, which I think they're equipped with up to 10 lasers or even more, that they're working at the same time, and it enables making big objects, or maybe 14 lasers if I remember well. For a series of that's what's on for Earth, but for space, when we think about, we don't think about serial production right now. We are thinking about technologies which enables the first steps. And what we need is as least as possible astronaut operational works, so automation, and also free-form fabrication technologies. So a technique that can almost create all type of geometries, from net shape objects, small size to mega size objects. So if you look at this, 3D printing is almost the best candidate among the other fabrication technologies with infrastructures that we need. And yeah, so it could be considered as a cost-efficient process for space production.
All right. And then I think there's another questions regarding how difficult is additive manufacturing in space in relative to on Earth? Aside from material use, what else do we have to consider in the process?
So post-processing, you know, lots of these methods, for example, if you need support structure, you have to remove the support structure. Sometimes you have to polish the parts in order to get the good surface finish, surface roughness that you need. So these are things that can be done automatically, but not all of it. So you need really either astronauts to work on that if it's smaller parts to handle, or you need lots of robotic infrastructures. That's I showed you the interlocking elements. Like we need robots to take those elements from the printing station, go and plant it on the roads. So we need lots of robotic work, or let's say Industry 4.0, which we have. We're working on that here, but you need the Internet of Things on the moon, which will take care of everything. Yeah.
Oh, it's pretty impressive to know. I think I got another questions from the committee member. They ask, for students interested in pursuing a career in this field, what educational path or courses do you recommend?
I mean, if you want to enter in the space industry, it doesn't matter what you study. From art, we need artists. From medicine, from biology, there are, you know, we want to understand the universe at the end, right? So any field is related. You can relate it to space. Psychology. What's how astronauts will react to isolation when we travel 9 months to Mars, when they don't see the light anymore, when you can only communicate physically with 5 person and then one closed capsule. To cinema, to everything you can. If you're interested, just I think you can find a job. Go for it. It's passion, and that's it.
True. Passion is everything. When
Yes.
we give it to you, true. It's true. I agree. And then I think there's another questions from our committee members again. They ask, to be where you are right now, have you ever encountered mistreatment or gender inequality in your field? If so, how have you navigated and addressed these challenges? Since we're women, after all, in the
Yes.
industry of mechanical.
Yes. So I completed my whole study in Germany, and I am now appointed, as you introduced me, as professor in Aalen. Right now, I'm sitting in Faculty of Mechanical Engineering. Yes, College of Engineering in Chala, which I really like it here. So regarding your question, so I think independent of gender, you always have some challenges in your work, which everybody faces. Now, for women, I can tell you a story which might be funny. During my PhD, I wanted to do some laser melting experiments under vacuum, which I found a machine somewhere far from our university in another city. It was a laser welding or laser manufacturing institute. And I entered this institute. I started working. Everybody was really nice to me, but I haven't noticed that everyone is man, and I was the only one. And I wanted to go to bathroom, to washroom. I was looking for the toilet for women, and I couldn't find it. And I asked the guy and said, Miranda, we didn't have any woman yet here, so we have only one toilet for men. So you know, it's sometimes you find yourself lonely on the path, alone, but it's not the end. I mean, it belongs to the path. If you're passionate about it, go with it, and there will be doors always open. After each door that you unlock, there will be a new door, and there is no end for it.
Wow.
Thank you.
Having no women bathroom, I couldn't imagine. My God. All right. I think there's another question for from another committee member. They ask, how do you go about selecting material for additive manufacturing in space, considering factors such as weight, durability, and temperature resistant? And how does everyone come up with the moon sand?
Could you please repeat the question again?
They ask, how do you go about selecting materials for additive manufacturing in space, considering factors such as weight, durability, and temperature resistant?
So selecting material is directly dependent on the application. So as this person mentioned itself, if it's on the ISS, we have another sort of environmental gravity conditions. On the moon, we have another sort of thermal cycle. So these are the things that you have to keep in mind. How did we come up with the moon sand? So there is a concept which called in situ resource utilization, ISRU, ISRU, for on-site manufacturing, which if you look back on the Earth's history, so we had cavemen, which started living in caves, which was already available, right? So we have these lava tubes also on the moon. The time of presentation was not enough. One strategy will be that we could use those lava things, the same that we did here on Earth. And then we started to use the resources on Earth to make small houses. So first houses, maybe we used wood. These biostructures are not available on the moon. And then we started to make concrete objects by sand, basically, putting stones beside each other. This is also a concept we can think on the moon, how to use the stones there. And then is the sand. So we took the sand and mixed it with the binders or melted it. So this is basically the same structure, the same path that we had on Earth. And the surface on the moon, if you look at it, if we go 30 centimeter deep, it's covered with the loose sand. And the particle size is less than 1 millimeter. So it's like a beach sand things from the feeling if you have in hand. So if you want to use stones, we need lots of mapping to see where are they more located, how big they are, how we can extract them. It was easier to think, okay, we have lots of sand structures, what can we do with it? So that's how we got with the idea of using moon sand.
Oh, I see. And then finally, we got questions from YouTube Live. They ask, are the 3D printed objects as of now acts more as a temporary solution rather than permanent fix?
For the space, if you mean for the space, they could be seen as both. For temporary solution, yes, we can have spare parts. For example, if something from a robot or rover, it fails, right? So temporary, we can replace it with a 3D printed part, for example, and the real part will be then delivered transported from Earth or somewhere else for short term, and for making habitats and for making roads, landing pads, then it's the long-term solution that we are aiming at, yes. Okay. I have to what? Okay. To video. Okay. I see also one question in the chat.
Yes, from Amir Baharu.
Yes, aside from the spacesuit, what is the possibility of additive manufacturing on aerospace part itself on the moon? So, like landing pads, building habitats, all possible infrastructures that we need on the moon. Also for mega scale structures, I say habitat, landing pads, and we can use it also for the spare parts, depending on which technique we are using. Like I showed you printing of flexible products, for example, as a texture, as a container, cable management part, things like this.
And I think this is the last questions I got from the WhatsApp committee. They ask, are there specific skills or knowledge areas that students should focus on to excel in additive manufacturing in space?
I mean, if you have a mechanical engineering background and knowing a little bit about the electronics, mechatronics would really help you. Also material science, how to evaluate the mechanical properties of the parts. So then overlap, well, I would say what you need is overlap of mechanical engineering, mechatronics, material science, and of course, if you're enthusiastic about the space, so you can always, you know about the lunar environment, gravity, but the three most will be mechanical engineering, mechatronics, and materials.
Right, guys, is there any more questions? Or we could end it. All right, I think if there's no more questions from participant, right? Or you guys will regret. Okay, so I would like to invite IR TS Dr. Muhammad Shukri bin Hadi and TS Dr. Norbaya Haji Side, which is our student welfare. Or sorry. My bad. I would like to invite IRTS Dr. Muhammad Shukri bin Hadi and TS Dr. Nobaya Haji Side, which is our Coordinator Professional Program, College of Engineering UITM, and Associate Professor TS Dr. Nobaya binti Haji Side, which is our Head of Leadership Student Development of College of Engineering, to hand over the Certificate of Appreciations to Prof. Dr. ING Miranda Fateri. Give a clap, guys. Put on the clap emoji. Yes. Since Professor Dr. Miranda herself flew from Germany, time in Malaysia, just 4-hour talk. Yes. Oh yeah, guys, later on we got back. So easier for you all punya certificate. Siapa tak isi, tak ada certificate. Gitu. Before we end our event, I would like to invite everyone for a photography sessions and participant. You may carefree to open your camera now. Join me. Let's have a photography session, guys. Yes, buka kamera. AJK. Silakan anak-anak buahku. Wait, let me set layout. Read. All right. Anyone want to open cam? Open cam. Open cam. Any more? Open cam. Cepat, faster, faster. Open your cam, guys. Jangan malu-malu. Don't be shy. Let's have a pictures once in a lifetime with professor from Germany, guys. Don't miss it out. If it's me, I really won't miss this chance. Once in a lifetime, guys. Dah semuanya. Belum? Ada lagi? Yeah. 1, 2, 3. Smile. Smile, smile, smile. Stay smiling. Okay, again. 1, 2, 3. Smile. Again. Last time, last take. 1, 2, 3. Smile. All right. Thank you everyone for your cooperation. So ladies and gentlemen, as a saying goes, to every beginning there is an ending, and our ceremony has come to its end. Once again, thank you everyone for gracing our event with your presence, and forgive us for our shortcoming. To all participants, kindly fill out the feedback survey as your final step to claim your certificate of participation. I, Dayang Fazira binti Awang Simon, will end my duty as Master of Ceremony for today's event with wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh. Bye.
Bye.
Jangan lupa.
Bye.
Bye. Easy feedback, guys. Scan the feedback survey for your certificate. You're welcome. Why is your name your ID? You should put on your name so I could like mention your name. You're welcome. You're welcome. From Aina saying thank you, Pro, and thank you everyone. You're welcome, Aina. Muhammad Yadi saying thank you, Prof. You're welcome, Yadi. Hakim Muhammad also saying thank you. You're welcome, Hakim. You are error. For real? Let me see, guys. Anyone have same problem? Error? Error ke semua orang? Cuba korang pakai link ni. So, kita forwardkan.